question 1, we know the limit of sine x over x is 1 when x is approaching 0. Okay, so don't confuse this with limit when x is approaching infinity. Right? When x is approaching infinity, we can use a squeeze theorem to prove that this is 0. Okay, but here we are when x is approaching 0, we're going to use this. Okay. Part 8. What is the limit of sine x squared over x squared? Right. So it's also sine something over something, and this thing is approaching 0, right? So it should be 1. And if you're not clear, you can use this substitution, let y equals x squared. Right? Let y equals x squared. So this equals limit, let y equals x squared. This equals limit sine y over y, right? And when x is approaching 0, y is also approaching 0 because y is x squared, right? So if you're not so clear directly from here, you can do one step substitution, and from here it is quite clear, it's 1. Right? So from here on, I will not do the substitution. Okay. So part B is sine 3x over x. Okay, so here it's sine 3x, so I want a 3x here. Right? So I multiply 3 on the bottom, so to balance it, I have to multiply 3 on the top as well. Right? Then it's 3 limit sine 3x over x, 3x. When x is approaching 0, 3x is also approaching 0, right? So this sine 3x over x, it's also approaching 1. Okay. Sine x squared over sine x over sine x. So here, the top is x squared, so I want an x squared on the bottom, so I have to multiply x squared on the top. Right, but here bottom I have sine x, so I want x on the top, so I can write it as times x times x. Okay, so this becomes, right, because all these three limits exist, so it's a limit of this over times the limit of this times the limit of this. Right? So because all three limits exist, so you can split the limit. And now this is 1, this is 1, this is 0. Right? So the answer is 0. Okay. Part 4. Part D, limit x is approaching x. So x is approaching pi, sine x minus pi over x minus pi. Right. So here, x is approaching pi, so x minus pi is approaching 0. Both parts are approaching 0, right? So you can write down it's 1. If you're not that clear, you can do one-step substitution. You can let y equals x minus pi. Then here, limit when x is approaching pi, right? When x is approaching pi, your y is approaching pi minus pi, it's approaching 0, right? So your y is approaching 0. Sine x minus pi is y over y. Right? And this is quite clear. It is 1. Limit x approaching 0 sine x over x. So sine something, the sine theta, right? The denominator, it should be this theta. So you want a sine x here, and you have x here, so you want the numerator to have a sine x. Okay, then these two cancel out, so it doesn't change anything, right? So this part exists, so we can, and this part exists, so we can split the limit. So it's a limit of sine x over sine x times, right, this part, sine x over x. And this part is sine something over something, and this thing is approaching 0. So we can use, if you're not clear, right? If you're clear, it's just 1. Right? If you're not clear, you can use one-step substitution. Only for this limit, it's y equals sine x here. So it's right, sine y over y. And here, x is approaching 0, so sine y is also approaching 0. Right? So y is approaching 0. So this is 1. Okay? Then this is 1. So it's 1 times 1. Okay. Part F, limit x times sine 1 over x. X is approaching positive infinity. Okay, so here, so we can rewrite it as sine 1 over x over 1 over x. X is approaching positive infinity. And we can, because when x is approaching positive infinity, this is approaching 0, this is approaching 0 from the right, right? So we can let y equals 1 over x. Then here it's limit when when x is approaching positive infinity, your y is approaching 0 from the right side, right? So it's limit y approaching 0 from the right side, sine y over y. Okay, and this is 1. Okay, so that's for this problem.